Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And today we're going to be talking about differences in the weather between the northern and the southern hemisphere. And there are some notable differences, and so we're going to talk about that and the highs and lows of all of it. Okay, so let's take a look at a schematic here of the Earth, and I'll get out of the way. There we go. That's the equator on the left, okay, and the North Pole on the right. Now, we've talked about this before, where in meteorology in the upper atmosphere, above the ground, we talk about surfaces of constant pressure. In other words, everywhere along that surface, the pressure is the same thing. So let's say that we have a constant pressure surface of 1,000 millibars just above the ground, okay, and it's fairly flat. Now, above that, we have a constant pressure surface of 500 millibars that is rather severely tilted. Well, why is that? Well, we've talked about this concept called thickness between two surfaces of constant pressure. If the air is warmer, then those two surfaces have to be farther apart. And if the air is cold, then they have to be closer together, which sort of makes sense, right? Because warm air is less dense than cold air. And so you're going to have the air at the equator spread out over a greater distance than at the North Pole, where it's rather cold and rather dense. And so with the 500 millibar surface tilted the way it is, then we have higher pressure here and lower pressure here, okay? So the pressure gradient force, which is what drives the wind, goes from the equator toward the North Pole. And if the Earth didn't rotate, then all the winds would go from the equator to the North Pole and from the equator to the South Pole. But of course, it's not that simple. So here we have the Earth again. And here we're looking down on the Earth on the North Pole, okay? So here's the equator out along the edge, and the North Pole is in the middle. So you are directly above the North Pole looking down on the Earth. Now, the Earth is spinning at the same rotational rate, if you will, everywhere. But think about this. At the equator, it has to cover all of this territory, all the way around this big circle, okay, in the same amount of time that it is traversing this much shorter distance around this circle, and the same amount of time that the air is traversing, or the Earth is traversing this even shorter distance around this small circle. And once you get to the North Pole, then you have no speed at all because it's rotating around about that axis, so there's no distance traveled and there's no speed, okay? So the speed of the Earth at which it rotates is much greater, or is greatest, at the equator, and then it gets slower and slower as you head north, okay, toward the North Pole. I hope that makes sense. So the speed has to be greater at the equator because it's covering way more territory than at any other latitude line, but it's doing it in the same amount of time. So it does turn out that the distance to the center of the Earth from the outer edges does vary by just a teeny little bit as you go from the equator to the North Pole. And so the Earth is widest at the equator, and it's squished a little bit at the poles, but it's rather insignificant. Now, if you were to take a cross-section, like if this is the Earth, like this, and you're going to take a cross-section and slice it like this along latitude lines, okay, then the distance from the edge of the Earth to the center decreases markedly as you go north. It is fattest, okay, at the equator, almost 4,000 miles. By the time you get to 30 degrees north latitude, it's about 3,400. Then it really drops to about 2,000 at 60, and by the time you get to the North Pole, of course, the cross-section is 0 because there's no distance to the circle or no radius to the circle at all. So when you multiply this number here times 2 pi, if you remember your circumference formula, then this is what you get. The circumference at the equator of the Earth is almost 25,000 miles, whereas at 30 degrees north latitude, it's 21,000. At 60, it's 12,000. And by the time you get to the North Pole, it is 0. So if you then take that distance and say, okay, it's going to traverse that distance in 24 hours, this is the speed you get. The Earth is rotating at 1,038 miles per hour at the equator. And then as you head north, it gets slower and slower and slower and slower until you get to the North Pole where there's no speed at all. So when we talked about, I think we used this as an example one time, where supposing you have the world's strongest arm and you're in Miami and you're playing baseball with your dad, you're playing catch with your dad, and he's up in New York City, and you've got an arm strong enough to get that ball all the way from Miami up to New York. Well, because at the equator you're moving faster than your dad is up in New York, when you throw that ball, by the time it gets up to that latitude, it's going to land way to the right of your dad because you're moving from west to east a lot quicker than he is, okay? And so the ball ends up landing in the Atlantic Ocean someplace, okay, as opposed to getting to your dad. So let's go on ahead and talk about this from a slightly different perspective now. So we know that the pressure gradient force goes from the equator toward the poles, okay, on both sides, and then the Earth's rotation bends that 90 degrees to the right. And so here you've got the equator, and the pressure gradient force is going from the equator to the North Pole, and then the Coriolis force turns it to the right, and so we have prevailing westerlies in the northern hemisphere. Well, what happens in the southern hemisphere? Well, the pressure gradient force is directed from the equator to the South Pole, but now, because the momentum is greatest along the equator and least at the South Pole, it rotates to the left. And so both hemispheres have prevailing westerlies, even though the Earth's rotation actually has opposite effects from one hemisphere to the other. Now, what about individual highs and lows? How does that work? Well, in this case, we're just going to take the example of the high, and then you can take the opposite of that, and that'll work for the low. So the northern hemisphere on the left, southern hemisphere on the right. Here's your area of high pressure in both circumstances, and the pressure gradient force is always directed from high pressure to low pressure. So that force is going to go out from the high in all directions, okay? And the same thing in the southern hemisphere. No difference here at all. But we just showed that in the northern hemisphere, the Earth's rotation, which is the Coriolis force, turns everything to the right 90 degrees, and in the southern hemisphere, it turns it 90 degrees to the left. And so you have a clockwise flow around a high-pressure area in the northern hemisphere, and you have a counterclockwise flow around high-pressure areas in the southern hemisphere. And the lows are exactly the opposite. In the northern hemisphere, they're counterclockwise. We're used to that. But believe it or not, in the southern hemisphere, around a low, it is clockwise. So everything still moves from west to east, but the way the air rotates around high and low pressure areas is exactly the opposite in the southern hemisphere as opposed to the northern hemisphere. And to be honest with you, I'm not quite sure I could get used to that. I think I'm gonna stay right where I am on that one. So last but not least, you may have heard this idea that, oh, because of the Coriolis force and the Earth's rotation, that when you flush your toilet, it turns in a different direction in the northern hemisphere than it does in the southern hemisphere. Is that really true? No, it is not. The short answer is no. And the reason is that toilet flushing operates on way too small of a scale to be affected by the Earth's rotation. This is something that is, affecting areas of hundreds of thousands of miles, or hundreds of miles or thousands of miles, but certainly not on the order of the scale of a toilet, which is maybe a foot or two across, okay? So the Earth's rotation has no effect on that, and so we might as well just flush that idea right out the window. Okay, that is bonus weather video number 2 for this week. Hope that made a little bit of sense. And we will be back on Monday with another daily weather update. And, of course, another bonus weather video will be coming up next Tuesday. So we hope you'll join us for both of those. In the meantime, happy Easter weekend. Hope you have a chance to visit with family and have a good time with all of that. And then we'll see you back here again on Monday. So take care, everybody, and happy Easter.